Hello, chemists. Today we are going to be discussing a little bit about how acids and bases work and working towards introducing a new K sub something constant. I know you're excited. So first thing I want you to do is I want you to write down a definition of an acid or base. Pause the video and write down whatever your current definition of an acid or base is right now. Or if you think you can remember it, I'll let you off the hook for writing it down. All right, if you are back with your definition for an acid or a base written down, we're going to move on into what the definition we're going to use in this topic is. The definition we're using in this topic is to do with protons and whether a given substance is a proton donor or a proton acceptor. And that it is restricted to acid and base in aqueous solution. So if we're dealing with an acid or base in any other format, this doesn't apply, but that's okay because those are all we're dealing with in this class. We are defining an acid as something that is a proton donor. And this says H+. You may be wondering why this says H+ when it says proton right here. I want you to think about what an H+ ion looks like. So hydrogen, if we look at the periodic table, has one proton, no neutrons, and one electron. If we remove an electron to make it a positive ion, it becomes just a proton. It doesn't have any neutrons, so all it is a proton. So an H+ ion is a proton. So acids are things that are proton donors. So that means that they give away a proton. So the proton goes from the acid to the base. And we have an equation that looks like this. HCl plus H2O reacts to produce Cl minus and H3O. This H3O is called hydronium. And that means that a base is the opposite when you've removed a proton. Or sorry, when you've gained a proton that has been removed from a base. So when you have an acid, you remove a proton from it, and the thing that you have left behind is called the conjugate base. So acids are paired with their conjugate base. Acid turns into its conjugate base. And the other way around is also true. Bases are proton acceptors, and each base has its conjugate acid. So we've got this base here, CO3 2-. You can see that it is happy to accept a proton, and it accepts it from this H2O right here to give us a HCO3, which is the conjugate acid, and OH- is the base that's left over when the water gives up a proton. And this confusing diagram basically illustrates that. So you've got an acid that has its conjugate base and a base that has its conjugate acid. So acid conjugate base, base conjugate acid. And this is basically the same thing going on, just with different compounds. The important thing to remember is that there's always going to be four things. There's going to be an acid, a base, conjugate base that pair with their partners. And you may have noticed in the previous slide that water was acting like an acid and a base. That's because water is something that is called amphiprotic. It can act like an acid or it can act like a base depending on the circumstances. Amphi is a Greek word meaning kind of both. If you think of amphibians can live on land or in water, water is amphiprotic, like an amphibian. It can donate or accept a proton. Amphi meaning both, protic meaning proton. Water is the main one that will interact with, but there are others. But we'll pretty much always be using water in this situation. When water donates a proton, it becomes hydroxide. When it accepts a proton, it becomes hydronium. So a couple of more terms. We have strong and weak acids and bases, and you have encountered these before. We talk about them in year 12. There's a short list of strong and weak acids and bases, there's a short list of strong acids and bases. Anything that's not on that list is weak. Strong acids are defined as things that totally dissociate into their component parts in a solution. So if we take this HCl, HCl is a strong acid. It means that every single molecule of HCl will separate into H+ and Cl-, which is what we see here. HCl dissociates into Cl- and H+, but that H+ immediately attaches itself to the water to become H3O. So strong acid means it totally dissociates. Every single molecule separates. For every 1 mole of hydrochloric acid, we have 1 mole of chlorine and 1 mole of hydronium. For every, and a strong base is the same thing, but a base. The only strong base we need to deal with is sodium hydroxide. These are 3 of the most common strong acids. And in previous years, we just kind of left it at that. Strong acids mean they totally dissociate. Weak acids mean they do not totally dissociate. So last year we just said the concentration of the conjugate base of a strong acid is just going to be the same as that acid. This year, we are calculating how weak the bases are. So we can work out whether a base is weaker than another base or not, whether an acid is weaker than another acid or not. Strong acids are always just strong. All right, you may encounter these arrows right here. Almost every single equilibrium solution we're going to see has got this double-sided arrow that we're familiar with. That indicates weak acids or bases because it's moving in both directions. If we're dealing with something that is strong, something that fully disassociates, that is not at equilibrium, it goes to completion. So it's just got a single arrow. But if we have something that is pretty strong but not totally strong, we can have these kind of weird arrows where one arrow is strengthened or weakened. All 3 of these indicate that equilibrium lies to the right. You may see these. Do not use them. Only use this type of arrow right here or this type of arrow right here. Don't use these right here. That is all I'm going to talk about today. I'm going to leave it right there.